They call it a Type 6 civilization. It's the final level of a futuristic scale that measures how advanced a civilization is. It's called the Kardashev scale. But who made this scale and why? And yeah, how does our human civilization rank on it? We owe the scale to Nikolai Kardashev. He was an astrophysicist and one of the best radio astronomers of the past century. He got interested in astronomy at an early age. The future scientist worked hard and earned his PhD in 1965. Then he published an academic paper that introduced the scale with his name. Fellow astronomers got interested and expanded Kardashev's scale. At first, the scale only had 3 types of civilizations. One of the people that modified the scale was Carl Sagan, the famous American science writer. The key word to understanding the Kardashev scale is energy. Possible societies from other planets are measured by the amount of energy their technology uses. The more energy a civilization is able to harness, the more powerful the signal it can send. This means we would be able to detect them first. The principle is quite simple. Imagine you were stranded on a desert island. If you manage to light a fire, there's a high chance a plane or a ship will spot you. But imagine you had a signal flare. It would go high in the air, so it would be easier for the search party to find you. Kardashev's scale measured transmission distance in theory. Think of this radio signal as the flare I've mentioned. The most technologically advanced civilization would be able to send the signal the furthest. The more energy a proposed civilization had, the more powerful it was. The famous astronomer decided to rank civilizations in this way. A Type 1 civilization is also called a planetary civilization. A suitable name, as this civilization only has the capacity to harness energy from its home planet. This includes the energy that reaches the planet, such as sunlight. Another form of energy is one the civilization can produce itself. Think of power plants, wind farms, and hydro plants. Sounds a lot like Earth, doesn't it? Yeah, not quite. You see, we are not even a proper Type 1 civilization. Carl Sagan ranked Earth as 0.72, not a full 1. In comes Michio Kaku to explain. This theoretical physicist is one of the best-known popularizers of science today. In his mind, a Type 1 civilization should be able to control the elements, such as volcanic eruptions and the weather. This also includes those nasty shakings of the Earth. Humanity can't even predict these, let alone control them. Ocean cities are another example of technological achievement. For now, underwater cities are something that we can only see in movies. That's why Michio Kaku believes that Earth won't reach Type 1 civilization for at least a century or two. This stage in the development of civilization includes the complete use of resources on the planet. From the energy of the sun to the minerals hidden underground. Then this society would be kinda ready to upgrade. A Type 2 civilization would expand its search for energy beyond the home planet. That's why this type is called an interplanetary civilization. In terms of scale, this would mean using 10 billion times more energy than a Type 1 society. Sagan made this calculation. It would involve more than collecting the sun's energy using solar panels. Yes, I'm talking about going directly to the source. In theory, the best way to achieve this is to use a Dyson sphere. This is an engineering project on a massive scale. The idea is to encircle a star, like our Sun, with orbiting platforms that would form a sphere. The goal is to harness the star's energy and use the platforms as living space. Sounds out of this world, right? Well, that's because it is. The megastructure got its name from the American theoretical physicist Freeman Dyson, who first proposed it back in the 60s. He believed that the sphere would be the way possible extraterrestrial civilization would generate energy. If we spot one in outer space, there is definitely an advanced society behind it. For humans, the Dyson sphere might become a reality in 1,000 or 2,000 years. That's how far we are from becoming a fully fledged Type 2 civilization. That's a long time. I mean, 1,000 years ago, we were in the Viking Age, nowhere near the world we live in today. But wait till you hear how long it would take us to reach Type 3, a full 100,000 years. This civilization would go beyond its home and other planets. It would master entire galaxies. This far into the future, who knows if humanity would still exist? At least in the format we know of it today. Robots would probably be constructing Dyson spheres across faraway galaxies. Are you tired of getting stuck in traffic jams on your way to work every day? The laws of physics state that the fastest you can get there is at the speed of light. To us, this speed is astounding. But for future civilizations, this would be slow. They would need to warp space and time to go faster. Yes, exactly like the warp drive from Star Trek. Or they could develop wormhole teleportation. We are barely a Type 1 civilization, so we can only guess what a new technology a Type 3 will use to travel across the universe. This advanced society would probably be able to extract energy from black holes. Another possibility is that they could manipulate molecules. They would create new materials out of nothing. If such a powerful society exists, humanity should not hope to come in contact with them. So far, we are technologically inferior. Kardashev thought of Type 3 as the most advanced civilization possible. He didn't feel the need to further develop his theory. But other science enthusiasts didn't stop there. They expanded the scale with extra types. In the new scale, a Type 4 would harness the energy of the entire universe. They wouldn't need to live on a planet, but would inhabit black holes. The energy sources they would use are unimaginable to us. These societies would be so advanced that they would use laws of physics humans haven't discovered yet. So, is there anything left for a Type 5 civilization after Type 4 mastered the whole universe? Yep. Because who said there had to be just one universe? Their society would source power from multiple universes, that is, multiverses. At Type 6, a civilization wouldn't have to worry about energy. It would be so advanced that it could create universes. These beings would probably be able to control space and time. They would have the status of a deity. At some point, this civilization would probably become one entity, a supreme single mind that would control all existence. It would be the only one to understand what a more advanced type of civilization would look like. We Earthlings don't stand a chance of grasping the concept. But it's not all bad news for the inhabitants of the blue planet. We have the possibility to move up the scale. Kardashev made the scale to measure civilizations beyond Earth. He gave our planet only as a starting point. We are advancing slowly, but every new power plant humans build is a step closer to a proper Type 1. Scientists estimate that every time we increase our total energy supply by a quarter, we advance 0.01% on the scale. This occurs every 5 years or so. Not a huge push forward, but we're getting there. The key to reaching Type 1 and beyond is renewable energy. Every now and then, scientists discover a new source of energy. Geothermal energy and offshore wind power are just a couple of examples. Each time we find a new way to power our world, we get a step closer to a planetary civilization. So far, the energy of the sun seems the most promising. There are already solar panels at the International Space Station.
Did you know that humans are real space people? You were born in space. Heck, even I was born in space. We were all born in space. But for humans to be here on Earth, so many conditions have to be precisely correct that it's highly improbable that we even exist. But we do. First, we, and any other space creatures who might be out there, have to live on a planet orbiting a yellowish white star, not a red star or a blue star. Not a blue star, because they burn out too quickly. In a few million years, there wouldn't be time for evolution to do its relatively slow magic and produce intelligent beings. Blue stars also tend to swell up and turn red. When they collapse and explode, it makes it highly unlikely that any civilization could prosper near a blue star. Red stars, which are by far the most numerous kind of stars, don't seem like good prospects for intelligent civilizations to orbit around either. Red stars are so cold and so dim that a planet that could grow a civilization must orbit very closely to the red star, which would expose the planet to intense deadly X-ray radiation. So, though red stars are the most numerous and appear to have many planets orbiting them, red stars are a no-go for hosting intelligent, civilized life like our own. That leaves the yellowish stars, about 10% of all stars. However, an important fact must be met before considering the possibility of intelligent life living around a yellowish star. That fact is that the yellow star must be a third-generation star. Only third-generation stars will contain sufficient chemical diversity to sustain advanced life forms. Each time a star explodes, heavier, more complicated elements are created. The explosion expelled these elements and eventually found their way into a nebula. Gravity within the nebula will gradually form the next generation of stars, and so on. Our bodies need calcium for our skeletons and teeth. Our brains need zinc to help create the electrochemical signals that make us move, feel, and think. Our blood needs iron. Therefore, our bodies need to have formed around a third-generation star, and a yellow one. Amazingly, Earth has all the different elements in the universe, all 94 naturally occurring ones, from hydrogen to plutonium. Maybe that's why we're here. And we have to thank our third-generation yellow dwarf sun for that. Why yellow? Because yellow stars burn very steadily by nuclear fusion without significantly changing brightness over billions of years. If our sun became just 6% brighter or dimmer, Earth would become too hot or too cold to sustain civilized life. Fortunately, Earth is in the habitable zone around the sun. The habitable zone is where liquid water can exist on a planet. But that brings us to the second condition necessary for intelligent life to live in space: the planet itself. Recent studies with the Kepler telescope have shown that 1/4 of all yellow dwarf stars may contain Earth-like planets in the habitable zone around yellow dwarf stars. That figure is somewhat debatable. It might be as few as 1 out of every 33 yellow dwarf stars, but that's still a lot of planets orbiting yellow stars in habitable zones. So let's consider the second essential component for intelligent life in space: the planet itself. The planet that would bear intelligent civilization must have many particular characteristics that aren't easy to come by individually, and even more rare to find in combination. Most importantly, the planet must have protection against the star it's orbiting. Because stars shine by nuclear fusion in their cores, gas in the outer shell of the sun, called the corona, gets blown off into space in what's called the solar wind. Our United States satellites take constant readings of the force of the solar wind, which is mainly electrified, ionized, hydrogen nuclei, along with a smattering of atomic nuclei from the many other elements found in the sun. It's not the atmosphere that protects Earth, it's the magnetosphere that stops or deflects the dangerous solar wind, causing aurorae when the solar wind is attracted to Earth's magnetic poles and electrifies the air of the upper atmosphere like a fluorescent bulb. Without a magnetosphere surrounding it, any planet, even those in habitable zones, would be toasted by a constant rain of ionized hydrogen nuclei from its star. A planet with life on it must have a magnetosphere strong enough to deflect the solar wind. Not every planet in our solar system has a magnetosphere. The gas giant planets, Jupiter, Saturn, Uranus, and Neptune, have magnetospheres, but gas planets cannot have civilizations. Of the solid worlds, only Earth and Mercury have magnetospheres, and Mercury is too weak to stop the solar wind because of its closeness to the Sun. Another protective shield that keeps the Earth safe from the Sun is its atmosphere. The atmosphere is about 300 miles thick, with most of it concentrated within just 10 miles of the Earth's surface. The atmosphere protects life on Earth from both the Sun's ultraviolet, UV, radiation, and X-rays. The gas, ozone, which is 3 oxygen atoms bound into a large gas molecule in the upper atmosphere, blocks most of the Sun's UV radiation from reaching the ground. The planet Mars, whose atmosphere is 1,000 times thinner than the Earth's, has no ozone, and the Sun's ultraviolet emissions have totally irradiated its surface. A planet must be able to stop the UV radiation from its star, so the specific composition of the atmosphere is critical for any planet to have an intelligent civilization. We've got it, but it is a rare and precarious mix. The planet must have some part of its surface solid to walk and work on. The planet must have a crust. It's pure science fiction to consider underwater civilizations or floating civilizations in the atmospheres of other planets. A planet's crust must have tectonic plates that move, This movement of tectonic plates creates the subduction of the crust. Subduction is when one tectonic plate slides under or over another, bringing the fresh matter to the surface. This renewal of the chemical properties of the planet prevents chemical equilibrium, where nothing is reactive. Earthquakes and volcanoes also contribute to the process of geochemical renewal. That's right, earthquakes and volcanoes are good. Subduction of tectonic plates, then, is another planetary essential for life. Mars doesn't have tectonic plate activity. Neither does Venus nor Mercury. Mercury is one big tectonic plate, but there's no ongoing plate activity other than slight shrinkage. One big reason these planets have no life is that there's no geochemical reactivity because there's no tectonic subduction. And that brings us to the Moon. Yes, the Moon. To say that the Moon keeps us alive may seem like a stretch, but the contribution of the Moon to life on Earth is essential. First, the gravity of the Moon as it moves through space with the Earth not only makes the ocean tides ebb and flow, it also helps the rotation of the Earth to churn or stir the magma inside the Earth. The motion of the magma inside the Earth, with its high metallic content, contributes to the creation of the Earth's magnetosphere. So, the Moon keeps us safe in space by helping Earth become a geodynamo and creating our magnetism. The Moon is the largest moon in the solar system compared to the size of the planet it orbits. Essentially, it's primary. Many people consider the Earth-Moon system to be a double planet, but that's another issue. Another thing the Moon does that keeps life safe on Earth is to hold the Earth steady. Because the Moon is gravitationally locked to the Earth, the Moon acts much like a balance pole does for a tightrope walker. Therefore, the Earth doesn't wobble very much compared to other planets. This wobble is called libration. If the Earth wobbled as much as Mars or Saturn, not only would our weather become chaotic, but farming might have been impossible. These rare or unique astronomical circumstances work together to make Earth habitable for humanity. Many other factors are not astronomical, such as evolutionary, biological, and chemical factors required for life to exist on Earth. The probabilities, or improbabilities, are multiplying. Taken all together, we are very, very lucky to be here. In fact, we're so lucky that we may have hit the jackpot. Considering all the possibilities, it's doubtful that anywhere else in the universe is as fortunate as Earth.
Dozens of spacecraft and hundreds of probes take off from Earth and head for our planet's twin sister, Venus. It's about the same size as the Earth and has around 80% of our planet's mass. The temperatures here are too high for humans, and it doesn't have the air we're used to breathing. But we went there because scientists recently found traces of phosphine gas, which suggests that life might be there. Phosphine comes from various microbes and bacteria, so humanity goes on this journey to discover this life. With our technology, a flight to Venus would take 3.5 to 6.5 months, but we finally made it. Spaceships are landing on the planet, and when the first humans come to the surface, they see heat-scorched deserts, lava lakes, and geysers of poisonous acid. And that's it. Scientists miscalculated the radio telescope data. Phosphine never existed on Venus. So we're going back to the rockets, and we're getting ready for a longer trip across our galaxy. The scientists believe that there's at least 36 civilizations in the Milky Way that are similar to ours. They could be living organisms completely different from us. They may have different bodies, different eyes. They may walk and talk in a very different way than we do. But an advanced civilization has several criteria: technological progress and the use of developed communication between individuals. So, these civilizations must explore space, build cities, and be able to communicate with each other as independent species. Let's look at our galaxy and find these civilized worlds. So, the Milky Way is a spiral of 100,000 light years from side to side. If a star is born at one end of it in a super powerful blast, the light from that event won't even reach the other end until 100,000 years later. There's about 100 billion stars, and near each of them, there may be worlds similar to our solar system. Let's try to find these habitable worlds using giant sieves. First, we look for stars that have a lot of iron. Such stars burn at the perfect temperature for the development of life. And the iron in the star system will help form the cores of planets that will be home to another civilization. We sift the Milky Way through our sieve. We see that there are too many stars that fit the description, so we need another filter. Now let's find stars that look like the Sun in this pile. The star must be about 100 times larger than the Earth and 333,000 times heavier. An important criterion is the age of the star. When a star gets old, it begins to expand and turns into a red giant. At this time, it can absorb the planets around it. The life of such a star can end with a huge blast that destroys everything around it. So the star we're looking for must be relatively young. Let's use our sieve again. There's fewer stars, but still that's a lot. Now let's focus on the planets. They should be in the habitable zone of the star. Not too close to a star because then the temperature would be too high for life to be born. And not too far away. Then the planet would just be an ice block with nothing living on it. The temperature of the planet must allow the water to remain liquid. Another filter is the age of the candidate planet. It takes time for an advanced civilization to develop. Based on the experience of Earth, scientists believe that it takes at least 4.5 billion years for any life form to evolve to the human level. So we're looking for planets similar to Earth or older. We use our sieve one last time, and voila! We have 36 worlds where an advanced civilization is possible. Scientists conducted this study and published it in April 2020, based on these very criteria. All that's left is to discover these civilizations and make the first contact. We can detect such a civilization by using radio waves that come from it. Suppose there's a planet A with primitive living organisms on it. Millions of years of evolution, and they'll become a civilization with advanced technology. Radio waves will be the way they communicate. Then the whole planet will emit radio waves like a star emits light. And here on Earth, we'll be able to pick up this signal with antennas pointed into space. But there's a problem with the distance between the planets. For example, planet A is 1,000 light years away from the Earth. When planet A starts emitting radio waves, these signals won't reach us until 10 centuries later. We learned to emit and receive radio waves in 1895. And if the civilization on planet A emitted a radio signal at the same time, we won't be able to pick up that signal until 2895. It'll be the same on planet A. We sent a message in the form of a radio signal into space in 1974. In this signal, we encoded our number system, human DNA, and information about our solar system. If there's an advanced civilization on planet A, they'll be able to receive this signal only in 2974, and we'd have to wait another millennium to get a response from them. Another problem with radio waves is that they don't look like a constant glow on the planet, but like a flare. Radio waves are only used at a certain stage of civilization. At first, it's the primary method of communication, but then we begin to use cell phones, cable TV, and fiber optics. And as technology advances further, our radio wave light begins to fade out. So we only have about 100 years of active radio use by civilization to find it. One day we caught a strange radio signal of an unknown origin. Its characteristics suggested that the signal was created artificially, perhaps by an outer space civilization or a passing starship. Further searches for this signal given no results, and this gave rise to many theories and arguments as to what it really was. It could have been a signal from Earth that reflected off a satellite flying through the sky, or it could have been the traces of a comet a few light years away. But let's assume it was a civilization from outer space, one of those 36 that probably exist. Now we need to make contact with them. So we throw our luggage into a rocket and head out in the direction of our suspected planet. Our rockets can fly at 17,600 miles per hour. That means a rocket could cross the entire United States in just 8 minutes. But even if an advanced civilization lived near our closest star, Proxima Centauri, it would take us about 73,000 years to get there. Even at the speed of light, it would take 4.2 years. So we need to solve the problem of space travel. Our scientists plan to reach about a quarter of the speed of light with a laser. A powerful laser beam from Earth will push a microscopic probe in the right direction. This probe could reach our destination in about 17 years. And in another 4 years, when the signal from it reaches Earth, we'll know if there's an advanced civilization. Another possibility for faster-than-light travel is the warp bubble spacecraft. The spacecraft would have to compress space in front of it and stretch it behind its tail. Then we'll be able to reach any point in the universe in literally a few seconds. But such travel remains a fantasy for us. Perhaps we can get to different corners of the universe through wormholes. They're shortcuts similar to tunnels, but there's one problem. These wormholes might be inside black holes. They're the most mysterious objects in the universe. They're so heavy that even light can't escape their trap. Our spaceships wouldn't stand the tension either. There's also a theory that Earth is unique because it was born under completely accidental circumstances. 4.5 billion years ago, our planet was a block of lava that began to cool and solidify, but its tranquility was broken by an asteroid the size of an entire planet flying by. The collision occurred at such an angle that the Earth was not completely destroyed, but part of the asteroid remained in our orbit. A heavy rock near our planet stabilized Earth's rotation, and the gravitational interaction with the giant debris caused our core to heat up. In addition, the asteroid brought a lot of water to Earth. Such a collision is extremely unlikely. It's like winning the lottery, many times in a row. But so far, we have no reason to believe life in outer space exists. Just as we have no reason to believe that there's no advanced civilizations in the universe, except for ours.